Different values, so that involves the JZ operator. So you really need a perturbation that commutes with all of them. Why does it commute with all of them? So you can see it in several ways. Let's do L squared. L squared is Casimir. It commutes with any Li. It doesn't even think about S, because it doesn't know anything about S, so it commutes with S. So L squared commutes with any Li and commutes with S. And L squared is an invariant commutes with R squared, because R squared is rotational invariant, so everything commutes with that. In order to do the other ones, you can also think in terms of this matrix, J squared over here and S squared and do all of them. You should do it and convince yourself that they all commute. So we can do this. If we can do it, it's good, because then we can evaluate these quantities. So let's do a little of the evaluation. So this E1 N, L, J, M, J is equal to. Let's evaluate the S dot L part by using 1/2 J squared S squared minus L squared. So that gives you a factor of H bar squared over 2 with this 2 over there. So you get E squared H squared over 4 M squared C squared. J times J plus 1 minus L times L plus 1 minus 3/4 times N L J M J 1 over R cubed N L J M J. Okay, that should be clear from the fact we have J squared minus S squared, that's a 3/4, spin is always 1/2, and L squared. This is known, it's equal in fact to N L M L, 1 over R cubed N L M L, which is equal, let me discuss that again, it's a little A0 L, L plus 1, L plus 1/2. Okay, so this is a known result. It's one of those expectation values that you can get from Feynman-Hellman or for other recursion relations. And this is always computed in the original uncoupled basis. So we seem to be in the coupled basis, so again, are we in trouble? No, this is actually the same, and it is the same only because this answer doesn't depend on ML, because these states involve various combinations of ML and MS, but it doesn't depend on ML, so the answer is really the same, so these things are really the same. Happily, that simplifies our work, and now we have E1 N L J M is equal to En0, this is yet another notation. This is the ground state energy here, mc squared n j plus 1 minus L plus 1 minus 3/4 over L plus 1/2, L plus 1. Okay, this is spin orbit. So again, much of the difficulty here is just making sure you're doing the perturbation theory right and working with the two bases correctly. But now we're in a good position. We can combine our results. We had, so here's what I want to combine. I want in principle to combine all things, all the terms. And we've calculated all the terms to some degree. So we saw the Darwin term only affects L equals 0. On the other hand, spin orbit really requires S dot L, and the states should be eigenstate, but not eigenstate, but should be acted on trivially by L. If all your states are singlets, L gives 0 on them. So actually, you have a little bit of an uncomfortable situation, because L, acting on L equals 0 state, will give you 0, but you still have the 1 over R cubed, and the 1 over R cubed has L dependences here, so it's 0 in the denominator, 0 in the numerator. The whole spin-orbit coupling doesn't seem to make sense for L equals 0. So most people say, physically, the spin-orbit coupling vanishes for L equals 0. It should not be there. But then something very funny happens. If you take a proper limit of this as L goes to 0, it gives you, for the spin-orbit result, the same thing as the Darwin result. So for L equals 0, the spin-orbit limit is actually the same as the Darwin. It's almost as if you say, oh, the spin-orbit has everything in it, but it's not legal for L equals 0, but the Darwin does it. So if I put together the spin-orbit and relativistics for L different from 0, I'm legal. for L equals 0, I should really sum relativistic and Darwin. But actually, it turns out that it's the same as summing relativistic plus spin orbit, because the limit of spin orbit for L equals 0 is equal to the Darwin. So we will just sum relativistic plus spin orbit, and that gives the result for everything, including Darwin, for L equals 0. So this is minor subtlety, but the end result is that we can combine it. So the happy thing as well is that we now can do this. Mj, delta H relativistic plus delta H spin orbit, and Lj Mj. Because whatever we calculated here was actually the same that H relativistic in the couple basis. And anyway, the spin orbit, we use the couple basis to get this number. So this thing, you can add the two results, and you get En0 squared over 2mc squared, 3 plus 2n, j plus 1 minus 3l, l plus 1 minus 3/4 over l plus 1/2, l plus 1. A little messy. Okay. Something very unexpected happens now. It's something that when you do the algebra yourself, you say, wow, how did that happen? Here is the issue. We are trying to compute the splittings of the hydrogen atom, and for this, as we said, in the couple basis, the degeneracies happen for a given value of n. So I'm getting good at doing this diagram now. So we're looking at a fixed n, and then you have all kinds of degenerate states for various L's and J's. So is there a better way to rewrite this formula? And you say the following. Suppose you think of some states of fixed J states. J. For example, this state, here's our L equals 1. Over here, I have 1, 2, 3. 3p 3/2 and 3p 1/2. Here I have 3d 5/2 because this is L equals 2. So 2 plus 1/2 and 2 minus 1/2. So I have here states of fixed J, two states with the same J, but they come from different L's. Because when you get a total J of some value, it can come from a lower L, L plus 1/2 gives you that J, or it can come from a top J, L, with L minus 1/2 giving you that J. So a given J value can arise from an L that is a half higher, or an L that is a half lower. So if for a fixed J, it may be that L is equal to J minus 1/2, or L is equal to J plus 1/2. Now look at this quantity. We'll call this whole quantity f of JL. Very astonishingly, f of JL when L is J minus 1/2, or f of JL when L is J plus 1/2, you can calculate it. Put L equal J minus 1/2 on that formula, and then put L equal J plus 1/2 in that formula. You'll say, it's going to be a mess. In fact, both cases are the same, and it gives you minus 2 over J plus 1/2. So the whole L dependence here, amazingly, is fake. There's no L dependence in this factor. It's a little strange. There's no L dependence because given J, L can be two values, and for those two values, that function gives you the same. It's one of those, like x squared gives the same for 1 and minus 1. This function, once you fix J, L can be two values, and it so happens that these two values give the same. So at the end of the day, this just depends on J. That's the most important result of this lecture. The whole structure, once you put relativity, Darwin, and spin orbit, just depends on J. And what is the result when you simplify this? Our result is that the fine structure ENLJMJ fine structure 1 is equal to minus alpha to the 4th mc squared 1 over 2 n to the 4th n over j plus 1/2 minus 3/4. Whole answer. All together. Darwin, fine, spin orbit, and relativistic. So, a few comments about this. People that look at the Dirac equation more seriously would have expected this result. It turns out that in the Dirac equation, the symmetry and the rotations, the generator of rotations, is exactly J, which is L plus S. That generates rotations, that computes with the Hamiltonian, so you should expect that the energy eigenstates are J eigenstates. So here we're seeing that, yes, they can be simultaneously diagonalized. The eigenstates can also be labeled by the J value. So the exact eigenstates in the Dirac equation can be labeled by the J value, and we're seeing a reflection of this. this means that the J multiplets are not going to be split. And there's going to be, moreover, some degeneracy. They're not split because there's no MJ dependence, and they are all going to be the same. So let me finish by drawing how the spectrum looks. It's very important to see that. This quantity over here, this numerical quantity, is always positive for any state in the hydrogen atom. You can see that because J max, the maximum value, so this is negative, so you need to know what is the minimum value of this quantity to see if it goes negative. The minimum value of this ratio is when J is maximum. The maximum J is when J is L plus 1/2 with the maximum L. So this is L plus 1 maximum, but L plus 1 maximum is in fact N. So the minimum value of this is 1, so it is always positive. As N increases, the corrections become smaller. So what happens? All the corrections are negative. So if you had the original states, they all go down a bit. Even the ground state goes down a bit. 1s1/2 is down. Because for n equal 1, you do get a state. Then what do you get? 2s1/2 is here. It's also down a bit. 3s1/2. So this is L equals 0. Then you have L equals 1. Remember, what did we have here? We have 2p1/2. And 2p3/2, because L equal 1 gives you J equal 3/2 and 1/2. Look, these two remain degenerate because they have the same N and the same J, and that's all that matters. So 1/2 and 1/2 have the same J, so they remain degenerate. 2p3/2 has a higher J, therefore has a smaller number, so it's lowered less, and it appears a little higher. So here you would have 3p1/2, and here 3p3/2. And the next state here is 3 D. Now you're combining L equal 2, so you get 5/2 and 3/2. The 3/2 is degenerate with these 3/2 because it has the same J, and the 5/2 is a little higher. 3d5/2. So this is our final picture. The hydrogen atom, all the states get pushed down. The various multiplets with different L, but the same J, are still degenerate. This formula has no L dependence, so these two are the same. These two are the same. These two are the same. Moreover, the J multiplets are not split. Every J multiplet has a collection of states with different MJ, but MJ doesn't appear. So this is your fine structure of hydrogen atom, and this is where you study in detail the Zeeman splitting and the Stark splitting. And we'll talk a little bit about them next time, as we will begin also our study of the semi-classical approximation. See you then. Good morning. Today's lecture will deal with Zeeman effect, and then we'll get started with a semi-classical approximation. So Zeeman effect is the last topic we do with respect to the hydrogen atom and the corrections of perturbation theory. And with WKB, or the semi-classical approximation, we begin a new chapter in 806. Zeeman effect. So this is an effect having to do with an atom in a magnetic field. It was discovered by a Dutch physicist, Peter Zeeman, who lived from 1865 to 1943. He was a Dutch. And the work was actually done in 1896, at a time where there was very little idea of quantum mechanics to be. And he got a Nobel Prize for it in the year 1902. So what he discovered was that spectral lines seem to split in the presence of a magnetic field. Now it's an old result, therefore 100 years old. Its explanation and understanding took about a couple of decades, because you couldn't do it without quantum mechanics. So nobody could quite figure out what had happened, but it was very, very important in its time. It still remains very important. People use the Zeeman effect all the time. In fact, it's used nowadays in studies of astrophysics, the studies of the sun, the sunspots. You know, there are places in the sun where the temperature is a little lower, and that's places where the magnetic field lines in the sun sort of break out from the interior to the exterior. And it's interesting because the sun produces this cycle of solar spots, and it happens because the sun doesn't rotate uniformly, has a different rotation speed in the equator, faster than in the poles. So the magnetic field lines that go from north to south in the sun get tangled up, and they start breaking up and doing all these things. So people want to know what is the magnetic field in the solar sunspot, and in fact, they observe that weak magnetic fields away from the solar sunspots, and then they see the spectrum of an atom, and suddenly, as you move inside the spot, the spectrum, the lines split, and they can measure the magnetic fields very accurately. They're of the order of 3,000 Gauss, 2,000, 3,000 Gauss, and it's pretty interesting work. So this Zeeman effect remains very important. So what is the Zeeman effect? We have a Zeeman effect here. Zeeman effect. We have the magnetic field interacting with the electron, and the electron now has two magnetic moments, a magnetic moment associated with the orbital motion. looks completely like the classical formula of the magnetic moment due to a particle that goes in circles. It produces a current, and that current is proportional to the angular momentum of the rotating particle. And of course, there's the magnetic moment due to the spin that has a factor of 2 here, this G factor we've discussed before, S. So H Zeeman, you put an external magnetic field into the atom, a constant uniform external magnetic field, and you have a minus mu dot B, so you have an interaction mu L plus mu S dot B. So this is E over 2 MC, that's the typical factor here, and a recognizable L plus 2S. So it's not L.